All right. So all of these criteria for aromaticity are what we call classical criteria. And I'm going to tell you about some exceptions to the rule as well. Right. So something that's aromatic has to meet these four properties. Right. It's got to be flat. It's got to be monocyclic, meaning made up of one ring. And I'll talk about some exceptions. Obviously, this is an exception right here. It's got to meet the 4n plus 2 rule, and it's got to be what we call fully conjugated. Right. Now, when we talked about conjugation before, what was the definition? That was actually a test question.
So. It's between a pi and a sigma bond.
So we had something like, let's see, if we had something like this, right, that's conjugated. But if we add another couple of carbons on there, even though it's conjugated, it's not what we will call fully conjugated, right? It's only partial, right? In order for something to be fully conjugated, you got to have a p orbital on every single carbon, right? So let's look at benzene. Benzene is the perfect quintessential aromatic compound, right? All of the sigma bonds are the same length. All of the pi bonds are the same length, right? And if you notice, it meets all the criteria, right? It's a single ring, so it's monocyclic, right? It is fully conjugated. There's a p orbital on every carbon in here, right? It's flat, and it meets the 4n plus 2 rule. So what is the 4n plus 2 rule? So the 4n plus 2 rule is you set 4n plus 2 equal to the number of pi electrons. All right. So how many pi electrons are in benzene?
6.
6. That's exactly right. You got each double bond has 2 pi electrons in it. So each pi bond, not double bond, each pi bond has 2 pi electrons. And so you got 3 pi bonds. And 2 electrons in each one. So benzene has 6 pi electrons. All right. So 4n, you set 4n plus 2. The way that you determine if something meets the 4n plus 2 rule, you set 4n plus 2 equal to the number of pi electrons. And then you solve for n. So in this case, n is going to be 1. N has to be a whole number. If n is not a whole number, then whatever the molecule you're looking at, it doesn't meet the 4n plus 2 rule. All right. Any questions about that?
Oh, yeah.
Go ahead.
What does the n variable stand for?
It's just a random variable. Okay. Right? But it must be a whole number in order for that rule to be met.
Okay.
Yeah. Right. It can't be a fraction, and it can't, obviously it'll never be negative, but it can be a fraction. So let's look at some of these other molecules. Let's look at the naphthalene molecule right here. And naphthalene it used to be, they don't use it anymore, but it used to be the principal component in mothballs. So naphthalene, does it meet all of the criteria? Right, it is flat, that's for sure. It's fully conjugated. You can see that if I need to change. If I put a p orbital on everywhere I see a pi bond, you can see that it has a p orbital on every carbon. All right. So it is fully conjugated. What about the 4n plus 2 rule? Does it meet that? How many pi electrons do I have?
5.
Let's see. We got 5 pi bonds, right? And 2 electrons in each bond. So this is a 10 pi system. So 4N plus 2, we set that equal to 10. And solve for N, right? N is what? Is that right?
Yes.
Yeah. So it meets the 4N plus. What's wrong with which one of the criteria does it not meet?
Fully conjugated.
Monocyclic.
No, it's fully conjugated. It's not monocyclic. So naphthalene is an exception, right? There's another molecule. Let me show you here. I'll erase that over there. If I have a molecule like anthracene, which is 3 rings fused together, sorry about that. It's early. So anthracene is also aromatic, even though it violates the rule of being monocyclic, right? It has a p orbital on every carbon. It's fully conjugated. It meets the 4n plus 2 rule, but it's not monocyclic. So there are some exceptions to that. There are some exceptions to these rules, but these are what we call the classical rules. All right.
It's a little early for a hat, isn't it?
Who? All right. Let's look at the next molecule. I'm just going to abbreviate this as CP. It's a cyclopentadienyl anion. Now, would you consider that aromatic? How many pi electrons do you have?
We have 4.
Like, keep in mind, if there's a lone pair on a carbon, it's in a p orbital. So it will be considered a pair of pi electrons. So how many do we have? 6. Is it monocyclic? Yes.
Mm-hmm.
And it's flat. And is it fully conjugated?
Mm-hmm.
Do you have a p orbital on every carbon in that ring?
Yeah.
Yeah. So it is. So this molecule is also considered aromatic. Right. Now, where it came from, the molecule that it came from is not aromatic. The way you get to that is to take cyclopentadiene, which is this compound, and then treat it with a really strong base. Let's just say KOH. All right. And that'll give you the cyclopentadienyl anion. So is this compound aromatic? What do you think? No, it's not, right? It's monocyclic, but it won't it won't meet the 4n plus 2 rule, right? Because 4n plus 2 would equal 4. And what else is missing?
Is that fully conjugated?
It's not.
It don't have a p orbital on every carbon.
Yeah, there's no p orbital on this carbon right here. Right, so the starting material is just cyclopentadiene to get to here. Right, so this is not aromatic. But if you do a proton transfer with a strong base, you can make it aromatic. All right. And then I'm just giving some examples of molecules that are aromatic. So this also will be considered aromatic. Can somebody tell me why? Let me pull the rules back up. Does this satisfy all the rules for aromaticity?
Not fully conjugated.
Is there a plus charge on that top carbon right here?
Yeah.
Is that right?
Yeah.
if there's a plus charge on a carbon, what that means is that it has an empty p orbital, right?
Mhm.
There's an empty p orbital on that carbon. Because what's the hybridization state of that carbon? Anybody? If it's positively charged, and there's a hydrogen there that's not shown.
SP2.
It's sp2. So that means it has an empty p orbital some on that carbon. So there's a p orbital there, and then we can put the p's all the way around, like so.
Mhm.
So is it fully conjugated?
Yes.
Yes, it is. It's fully conjugated, and it meets the 4n plus 2 rule, and it's flat, and it's monocyclic. All right. Any questions so far?
So for clarification, was the second one? It wasn't aromatic, was it?
This one?
Yeah.
Yeah, it is. It's an exception.
Oh, okay.
It's an exception to the rule. Let me put that. I'll put it here.
So are these all exceptions except for the benzene in front?
No. The anthracene is an exception because it's not monocyclic.
Oh, but everything.
I'm sorry, naphthalene and anthracene. These are exceptions.
All right.
And then this is an exception. Right? The reason it's an exception is because it violates one of the rules, but it's still considered aromatic. But the rest of them don't violate any rules. All right. Any other questions? There's one other thing I want to show you, which is here. And that is the case where something could be considered, it would be aromatic if it wasn't non-planar, right? Because one of the rules is that it has to be flat or planar. And you don't have that here. This is a case where the planarity is not there. So it has a p orbital on every carbon. It has 1, 2, 3, 4, 5 pi bonds, so 10 pi electrons. But it's not aromatic. It's fully conjugated, it's monocyclic, but it's not aromatic. What's the problem with it?
It's not planar.
It's not planar. And that breaks up the aromaticity, because if you look at the double bonds the pi bonds that are here, right, those p orbitals can't overlap, right? They can't overlap with the p orbitals that are here in this plane. Right here. Right, so those p orbitals are perpendicular to the other one. So it's kind of like let me see if I can draw it. It's kind of like this, where you have some p orbitals up here on the plane and then some pointed the opposite direction. Right, so that lack of planarity breaks up the conjugation and it breaks up the aromaticity. All right, any questions on that? On the rules for aromaticity?